right, sound check, sound check. Sound looks good. Let's see if video is coming in. Do I see my hand? Yes, I do. Okay, perfect. Let's put the headphones away and let's get started. So, sorry I'm a little late, but better late than never, I suppose. I think today is the day where we wrap up the projectile motion topic. I do have a little bit of a headache, so I might end up having to end things early, but we'll see. We'll see how far I can get, and maybe, just maybe, I will actually be able to do traditional office hours this time. It's been almost a month since the last time I did that. So hopefully I can last long enough to do that. So where did we leave things off last time? Last time I left you guys off with this problem, so let me find it in the book. So it says, a soccer player kicks a rock horizontally off a 40-meter high cliff into a pool of water. If the player hears the sound of the splash 3 seconds later, what was the initial speed given to the rock? Assume the speed of sound in the air to be 343 meters per second. That does look pretty good in OBS, so I think I have fixed the problem from last time. I've changed a little bit of the lighting in the room, and if I still run into trouble with that later in the stream, then I guess I'm gonna have to tweak some more settings. I did actually try and adjust the focus of the camera. I don't know how much that'll help, but I did make an adjustment to it, so there's that. Anyway, this soccer problem, so I kind of gave away the big hint for it, which is realizing that the 3 seconds isn't just the time it took for the sound to reach the player's ear. It was the total time between the rock falling into the water plus the time it takes for the sound of the splash to reach the player. So if we go ahead and write T sound plus, I guess I'll call it T fall of the rock is equal to the total time is equal to 3 seconds. That should give us our starting point. So what do we want to do? Well, in order to calculate the time it takes the sound to travel from here to here, we need to figure out what the distance is from here to here, and then combine that with the speed of sound, and that'll give us the time. Or we can combine the speed of sound with the time of the sound if we calculate it in another way, and use that to calculate this distance instead. So right now that doesn't look like something we can calculate right away. It might be better to try and calculate the time it takes for the rock to fall. So that's where I'm going to start things off. Let's find the time it takes to fall. Do I have enough information to calculate this? I should, because I know what the initial velocity is in the vertical. This is a situation where you have a vertical boundary, so we're going to be looking at our vertical equations to figure out how much time is spent in the air by the rock. We do know the initial vertical velocity, as I already said. We know the acceleration due to gravity. And we also know the total displacement associated with the fall is going to be negative 40 meters. That's 3 pieces of information. We can calculate the other 2 kinematic variables in the vertical. We only need one of them, which is the time. So Which equation should I use? First equation involves Vy final, which we don't really care for here. Third equation, same thing. Second equation might be our best bet. So if I do delta y equals Vy initial times t fall plus 1/2 the acceleration in y times t fall squared. That should give me what I'm looking for. We know Vy initial is going to be 0. So we don't have to solve a quadratic, thankfully. And negative 40 for delta y equals 1/2 of acceleration in y, that's 1/2 of negative 9.8 is negative 4.9. And then t fall squared, the negatives cancel, which is good because we're going to take a square root, and we need to have a positive number before we take the square root. 40 over 4.9. What is the square root of that going to be? Chat disconnected. What does that even mean? I've never seen that message before. Anyway, 40 over 4.9, if I take the square root of that, I get 2.857. And now it says successfully connected on the chat. I don't know what that's about, but if people have been posting in the chat, I haven't seen anything yet. Maybe I just need to refresh the page on my end. I'll try that in a minute. 2.857 seconds is the total time it takes for the rock to fall 40 meters. Okay. And if we know that, well, what was the question? The question was, what was the initial speed given to the rock? In other words, what was Vx? Because V initial was just entirely in the x direction. Okay, we can figure that out later. At least we now have the time it took to fall into the water. Let me go ahead and refresh this page and see if that'll at least make that scary message disappear. Looks like it. Okay, I don't know what that was about, but I'll keep an eye on things and hope for the best. Now then, we calculated the time it takes to fall, and we know the total time is 3 seconds between kicking the rock and hearing the sound of the splash, so the sound must have been traveling for 3 seconds minus 2.85. T sound must be 3 seconds minus 2.857 seconds is equal to 0.143, if I'm not mistaken. 0.143. I don't need the calculator for that. 0.143 seconds. Okay, sound travels at a constant speed, so all I have to do is multiply my constant speed by my time to get my distance. This distance over here call it d, can be calculated simply by multiplying d equals, I guess I can actually do it here, d equals v sound times t sound is equal to 343 times 0.143 is equal to 343 times 0.143, 49.049. I'll just round it to, well, okay, fine. I'll keep it unrounded. 49.049 meters. Maybe I should have boxed it instead of circling it, but whatever. Okay, so how does that help us? Well, that helps us because now that we know this distance over here, we've got two sides of a right triangle, which means I can calculate the third side using the Pythagorean theorem. Now that I know this is 49.049 and I know this is 40, I can calculate, let me switch colors. I can calculate this. I can calculate delta x. So it's going to be d squared equals delta x squared plus delta y squared. So 49.049 squared, 49.049 squared equals delta x squared plus negative 40 squared. Not that the negative matters here because when you square it, it's going to disappear anyway. So let's see, 49.049 squared and then minus 40 squared is 805.804401, and that's going to be equal to delta x squared. So if I take the square root of that, positive square root is 28.3866. I'm going to round that to 28.39. I'm going to say delta x is about 28.39 meters. And that's the positive root. I don't need to take the negative root because I'm just going to say that right is the positive direction for this problem. And now that I know delta x, and I know the total time that the rock was in the air, I know the total time that the rock was traveling horizontally, which means I can now just use, what color do I want for this? Let's do green. Now I can just use delta x equals vx times t, vx being the value we're trying to solve for, and the t in this case is just going to be t fall. The time it took to fall 40 meters vertically is also the time it took to travel 28.39 meters horizontally. So that's going to be 28.39 equals, well, Vx is just going to be all of V initial. It's going to be V initial times cosine of 0, which is just V initial since cosine of 0 is 1. So I'm going to rewrite Vx as just V initial. And then T fall was 2.857, 2.857. So it looks like V initial is very nearly 10. 28.39 divided by 2.857 gives me about 9.937. I'm going to say 9.94. So V initial is about 9.94 meters per second. And there you go, there's the problem we left off with last time. So the rest of today is just going to be focused on some more advanced projectile motion problems. We're going to pick some of the tougher ones, some of the ones that require more advanced algebra compared to what we did last time, and then hopefully we will wrap up the chapter here, and if we do, then next time will be the introduction to the topic of force. So without further ado, let's get started. Where do I want to start us off? Here we go. Here's the next problem that I want. Is the back? Yeah, the back side of that page is already used up. Time to grab a new sheet. Okay. So we have, this is another problem that I like to give every year to my students. It says a rocket is launched at an angle of 53 degrees above the horizontal with an initial speed of 100 meters per second. The rocket moves for 3 seconds along its initial line of motion with an acceleration of 30 meters per second squared. At this time, its engines fail and the rocket proceeds to move as a projectile. Find, Part A, the maximum altitude reached by the rocket, Part B, its total time of flight, and Part C, its horizontal range. So we need to find maximum altitude, also known as maximum height. So we need to find H max or Y max, if that's what you prefer to call it. Total time of flight, so I guess we'll call that just the hang time. And part C, we want to find its horizontal range. What is delta x max or delta x total, whatever you want to call it? All right, let's draw the situation. So we have the rocket was launched at an angle of 53 degrees above horizontal. I think I want to start pretty low for this. So here's 53 degrees above horizontal. And it starts with an initial speed of 100 meters per second. So I can already tell this is going to be the kind of problem that we have to cut into several segments. So I'm going to call this initial speed V0. I'm going to use numbers instead of just initial and final so that we can kind of keep things in sequence. So that's going to be V0 equals, what did it say? 100 meters per second equals 100 meters per second. Okay, rocket moves for 3 seconds along its initial line of motion. So it moves in a straight line for 3 seconds, and let's say the 3 seconds are up by the time you get here. With an acceleration of 30 meters per second. So I guess I'm going to list T1 equals 3 seconds, and acceleration for part 1 is equal to 30 meters per second squared at 53 degrees above horizontal. My light is flickering. That might be cause for concern. I might have to switch out the bulbs. You solve one problem, you run into another. Such is life. Anything else to glean from here, rather? Glean, not gleam. There's a difference between those two words. Glean with an N is to, how would I describe it? To like gain information, to have an insight or something like that. And there's that message again about the chat disconnecting and reconnecting. I don't know what that's about, but I'm not going to worry about it. Where was I? I was going on a little bit of a detour about vocabulary, but other than that, we're going to have, so once you get to this point, everything continues from this point onward as projectile motion, so we're going to have it go up, and from this point, the path is going to start curving, like what we've seen in our other projectile motion problems. Not drawn to scale, I'm pretty sure. It reaches a maximum height that's more than twice whatever this height is at this point. I could have made this look a little bit more curvy. Otherwise, this kind of looks like a full parabola, even though this part is supposed to be straight. Oh well, so I'm going to establish another point over here, split at the top. And I really should have drawn this even lower than I did. Poor planning on my part, but we can work with this. So I want to cut this into 3 segments, from here to here, from here to the top, and then from the top to the bottom. The reason that I want to split it at the top is the same reason that I did so when we were doing free fall, because you just get one piece of information for free, and that piece of information that you get for free at the top is Vy is equal to 0 at the top, which should be useful to us. Okay, so the acceleration, this 30 meters per second squared, it already has the gravity factored into it, so we don't need to do anything fancy with it. We don't need to draw like triangles and figure out what the total acceleration is or anything like that. This is the total. They figured that out for us. And they said that the object moved along its initial line of motion. If you remember what we discussed last time, when the acceleration is either in the same direction or in the exact opposite direction to the velocity, you will get a straight line path. So if they told us the path was a straight line path, then the converse is true. That must mean that the acceleration is either parallel or anti-parallel to the velocity. And of course here it wouldn't make sense for it to be anti-parallel. It would have to be just in the same direction as the velocity for that phase. So we can just use our regular kinematics here for at least this first phase of the motion, and we can calculate whatever this distance is. Whatever this, I guess, if I had drawn this a little further to the right, I would have had more space to write this, but this, I guess I will call it delta S. We can figure out what that two-dimensional displacement is. So let's go ahead and do that. I think we have all the information we need. We've got a velocity and a time and an acceleration. I can just use the second equation. Yeah, this should work just fine. So second equation, delta S is going to equal V0 times T1 plus 1/2 A1 times T1 squared equals V0 is 100 meters per second times 3 seconds plus 1/2 of 30 times 3 squared. Okay, so we have 300 plus 1/2 of 30 is 15 times 9. That's 435 on the dot. 435 meters. So this is 435 meters at an angle of course, 53 degrees above horizontal. Nothing too surprising there, I would imagine. Now, what we can do with that is we can use that 53-degree angle to figure out the delta y. And also, we can figure out the delta x. So we could figure out the delta y (1) and delta x (1). And I also want to figure out v1, because whatever v1 is, that's going to be the velocity that we start with for the next phase. So I want that too. Okay, well, the first question they ask us is what's the altitude, so I guess delta y1 we're going to need to calculate pretty soon. Delta x1 can wait because that's the last thing they ask us about. So yeah, let's get delta y1 and then let's get v1 so we can start the second phase of this. And I keep on getting that message about chat disconnecting and reconnecting. What is going on? Hold on. Let me see if this is something I can fix. Let me try refreshing the page first. Does that do anything for us? Yeah, it looks like it did. The video preview looks blurry, but it looks just fine in OBS. Well, hopefully the recording will turn out okay. And I don't see that nasty chat message anymore, but I have a feeling it's going to show up again anyway. Anyway, back to the problem. So we had, what was I looking for? I was looking for delta y1. I can just do delta s, which is 435, times sine of 53 degrees, and that will give me the opposite side, which is delta y1. And you know what, we might as well. 435 sine of 53, 347.406. So I'm going to say 347.41 is what I'll round it to. And might as well calculate delta x1 while we're here. 435 cosine of 53 gives me 261.789. I'm going to say 261.79. 261.79 meters. Okay, and let's figure out v1. We can just use the first equation of kinematics for that. Remember, we're just moving in a straight line for this first phase. So I can say v1 is equal to v0 plus a1t1 equals v0 is 100 plus a1 is 30 times t1 is 3. That gives me 190 meters per second. So v1 equals 190 meters per second. And because all this motion happened in a straight line, v1 is still at an angle of 53 degrees above horizontal. This means we can now break v1 because from this point onward it's projectile motion, so we need to break it up into components. The 53-degree angle, knowing that it's 53 degrees, allows me to break v1 into components. I'm going to call them vx1 and vy1. So let's do, I guess I'll write it over here, vx1 and vy1. Vx1 is v1 times cosine of 53, and vy1 is v1 times sine of 53. Let's see what those are. So Vx1 is going to be 190 times cosine of 53 degrees, 114.34. 114.34 meters per second. And then for V1, 190 times sine of 53 gives me 151.74. 151.74 meters per second. Okay. So I want to go from here to here. So up here, I'm going to be at, I don't even have the space for this. I guess I'll do a squiggly arrow. Over there, I'm going to have V2y is equal to 0. So the y component of the velocity at the end of the second segment of our motion, that's going to be 0. And I can now use that to calculate delta y2. I want to calculate delta y2. Delta y2. And I can use the third equation for this because I would have Vy1 and Vy2. I knew I did something wrong here with my notation. Vy2. I mean, I guess it doesn't really matter, but here. Vy2. There we go. Okay, fixed it. So third equation, Vy2 squared equals Vy1 squared plus 2 times acceleration of phase 2 times delta y of phase 2. Acceleration for phase 2 and for phase 3 is negative g, negative 9.8. So Vy2 squared, that's 0 squared, equals Vy1 squared, so 151.74 squared, plus 2 times negative 9.8, that's negative 19.6, times delta y2. Add 19.6 delta y2 to both sides, and whatever 151.74 squared is, divide it by 19.6. And I'm getting that chat disconnected, successfully reconnected message again. I don't know what that's about. If people are trying to post in chats, I'm not seeing it today, and I don't know why. Anyway, 151.74 squared divided by 19.6 gives me 1,174.746. I guess I'll round that to 0.75, so 1174.75. Delta y2 is equal to 1174.75 meters. Which clearly means that my drawing is not to scale. I'll write it over here too, just for clarity. 1174.75 meters. Okay, we can now answer part A. I guess I'll do it up there in the corner. Let's use this color. maximum height is going to be just equal to delta y1 plus delta y2, delta y1 plus delta y2 is equal to 347.41 plus 1174.75 equals 347.41 plus 1174.75 equals 1522.16. Equals 1522.16 meters. I'm still getting error messages in the chat. What is that for? I said I was going to forget about it. So yeah, I'll just forget about it. I'll ignore it and we'll figure it out after the stream is over, I suppose. And if it is what I'm guessing it is, then sorry to the people that were trying to ask questions. Okay, next part, so we're trying to calculate the total hang time, which means I'm eventually going to have to calculate T2 over here. I could calculate it right now. I already have enough information for that. And we're also going to need to calculate T3, the time it takes to drop all the way back down. Okay, well, we might as well calculate T2. So what do I want to use to calculate my T2? First equation, actually, yeah, first equation would probably be the most efficient. We know Vy2, we know Vy1, we know the acceleration for phase 2 is just negative 9.8, and that leaves us with only T2 as our unknown. So yeah, we can solve this. 0 equals 151.74 plus negative 9.8 times T2. So 151.74 over 9.8 is what I'm left with. And now the error message just keeps on popping up every few seconds. Oh my goodness, what is going on? I'm going to take a screenshot of this. Yeah, and that way I'll have something to refer back to for later, when I investigate what on earth is happening here. Anyway, 151.74 over 9.8. And I'm getting 15.4836. I'm going to say 15.484. I'm going to say T2 equals 15.484 seconds. And now to get T3. Well, to figure out T3, I already know Vy at the top. I don't know Vy at the bottom, and I actually don't need to know it. I know my acceleration in y is just going to be negative 9.8 for phase 3, and I can get my displacement for phase 3. Displacement is going to be from the top to the bottom. We already calculated the maximum height, so displacement for phase 3, delta y3, delta y3 is just going to be negative the maximum height, negative 1522.16 meters. So knowing that, I think the second equation would be the one to help us here. let me think. Delta y3 equals vy2 times t3 plus 1/2 acceleration y3. Come to think of it, I forgot the y over here as well. Plus 1/2 acceleration y for phase 3 times t3 squared. Okay. Vy2, that's a 0. So that means we don't have to solve a quadratic. We don't have to use the quadratic formula. So I have negative 1522.16 equals half of acceleration y3, half of negative 9.8 is negative 4.9 times t3 squared. The negatives cancel out. 1522.16 divided by 4.9 is 310 point a bunch of numbers, and then if I take the square root of that, it only makes sense to take the positive square root here, so positive square root is 17.625. 17.625. T3 equals 17.625 seconds. Okay, so we have this, and we have this. We've got T2 and T3, and we were given T1 from the very beginning. So now all we have to do is add those up to get our total hang time. Our total hang time is T1 plus T2 plus T3 equals 3 plus 15.484 plus 17.625 equals 36.109. Equals 36.109 seconds, give or take. All right, and that's our second answer, so I should have circled our first answer up there. And now we are left with the question of what is delta x max? Well, for that I need delta x1, which we calculated earlier, and delta x2 and delta x3. So I need delta x2, and I also need delta x3, and I want to add all of those together to figure out what my total delta x is. Something seems off about, oh, I drew the delta x1 too wide. Delta x1, yeah, delta x1 should have stopped over here, not, yeah. Sorry if I confused anybody with that. Anyway, the good news about delta x2 and delta x3 is that I don't have to calculate them separately, because for the entire, if I combine both the second and the third phases, delta x2 plus delta x3 can just be calculated all in one go. I guess I'll show what it would look like if we did calculate both of them separately. So what we would want to do is we would say delta x2 would be equal to vx2 times t2, and then delta x3 would be equal to vx3 times t3. And if I add those, delta x1 plus delta x2 equals Vx2t2 plus Vx3t3. But Vx2 and Vx3 are the same. There is no change in the horizontal velocity after the rocket engine is cut off. From that point onward, assuming no air resistance, there should be nothing causing a change in the horizontal velocity. So I can just factor out my Vx, which was... wait, did I call them Vx? Vx1 and Vx2. 1 and 2. Okay. Anyway, that little notational hiccup aside, Vx1 and Vx2 should be the same. They should be 114.34 for the entire time from the point the rocket engine cuts off until the rocket lands on the ground again. So I can factor this out and say that this is just equal to my 114.34 times T2 plus T3. And because we calculated the total time earlier, I can just take 36.109 and subtract T1, which was 3 seconds. T2 plus T3 is just 33.109, so this is just 114.34 times 33.109 seconds. And that gives me 114.34 times 33.109 is 3785.68. 3785.68. So that 3785.68 meters, that is the total horizontal travel after the engines are cut off. We then need to add delta x1, 261.79 to that. And if I do that, 3785.68 plus 261.79, I get 4047.47. So I get delta x total, delta x max, whatever you want to call it, is equal to 4047.47 meters. And there we go. Quite the long problem, especially when you have to slow down and explain it, but once you've practiced problems like this enough times, you can usually get through something like this in, I would say, under 10 minutes with enough practice. And I'm not even talking about rushing yourself or anything. It's just, I did this slower because I was pausing between my steps to explain my calculations. And also I slowed down, for example, over here to go over this shortcut, whereas if I was just doing it on a test myself, I would just jump right ahead to this. So yeah, even though it looks like it takes a very long time, it's actually not too terrible. Should be doable in like 10-15 minutes or less. Okay, where do I want to go next? How about this one? I think this one will be a little bit simpler. It says if a person can jump a maximum horizontal distance by using a 45-degree projection angle of 3 meters on Earth, what would be his maximum range on the Moon, where the freefall acceleration is g/6, where g is equal to 9.8 meters per second squared. Repeat this for Mars, where the acceleration due to gravity is 0.38 g. more than a third. I think I'll just do the moon one, and you can do the Mars version on your own if you're curious. Okay, let's pick this one. And they have a person. They said they jump at a 45-degree angle. And they achieve a certain horizontal distance of 3 meters, they said. The person achieves a 3-meter horizontal distance jumping at a 45-degree angle on Earth. So this is on Earth. How far would they get on the moon? You could probably imagine that on the moon, with weaker gravity, the person would be in the air for longer, which would allow them to travel farther. But the question is, how much farther? Twice as far? 4 times as far? 10 times as far? How much farther? So if they jumped at a 45-degree angle on the moon... Wait, what did I do? 45-degree angle. If they did this on the moon, they'd go higher, of course, and land farther away, but the question is, how much farther away? That is the question being asked here. So, I guess we're going to need to figure some things out. To figure out how far you travel horizontally, you need to figure out how long you travel horizontally. And you're traveling horizontally until you land back on the ground. So, we're going to need to rely on what happens in the y dimension to figure out how much time we get to have in both dimensions. For the Earth scenario, I know that over here, Vy top, or Vy apex, or whatever you want to call it, is equal to 0. So we can actually use that to figure out what the initial velocity even is. So I can say whatever my initial velocity is, it's going to have some y component and some x component, and at a 45-degree angle, the y and x component are actually going to be the same, only for 45 degrees. So I can say Vy initial is equal to whatever V initial is times sine of 45 degrees. And then I can do, I guess, first equation to calculate the time from here to the top. Actually, I could also just use, couldn't I just use the second equation? Let me think here for a minute. If I were to use the second equation from start to finish, delta y would be 0 there. No, I don't have enough information for that. Okay, so Vy initial equals V initial sine of 45 degrees. And then if I use my first equation to calculate the time to rise, then I would do Vy top, which is 0, equals Vy initial, which is V initial sine 45. Plus acceleration times time. So that's going to be negative g times t rise. And then if I solve that for t rise, I get, well, add gt rise to both sides. So gt rise equals v initial sine 45. Divide by g, and you get t rise equals v initial sine 45 over g. And then if I multiply that by 2, I get the total time, so the hang time equals 2 v initial sine 45 over g. And then that hang time I can use in my delta x equation. I can do, let me switch colors. I can do delta x equals vx times t. Vx is going to be v initial cosine of 45 degrees. So my delta x, which is going to be 3 meters, but I'll keep it as delta x for now, equals v initial cosine of 45 degrees times the total time, which is the hang time. So times 2 v initial sine of 45 degrees over g. Some of you might be seeing something familiar from pre-calculus here. Those who haven't had pre-calculus yet, or you're still in pre-calculus and haven't gotten to that part of pre-calculus yet, you probably don't know what I'm talking about, but it's okay. You'll learn it eventually. We don't actually need it here, but we will need it for a later problem. So I'm going to factor out the 2, and the v initial over here goes into that v initial to make a v initial squared. So I get 2 v initial squared over g times sine 45 times cosine 45 times cosine of 45. And those who know their trig identities from pre-calculus or trigonometry will know that 2 times sine 45 times cosine 45 is equal to sine of 90 degrees using the double angle identity. If you don't know what that is, don't worry about it. We'll talk about it later when it's more relevant. Here you can just plug into your calculator sine of 45 times cosine of 45, and you will get exactly 1/2. And then 1/2 times 2 is equal to 1. So we end up with delta x is just equal to v initial squared over g. And from there we can say delta x earth, I guess I'll start it here, delta x earth equals v initial squared over g earth. Delta x moon equals that same v initial squared over g moon. And if I want to calculate the ratio between them, if I want to calculate delta x moon over, moon, not mu, delta x moon over delta x Earth, then all I need to do is divide these two. So let's see, that would be V initial squared over G moon over V initial squared over G Earth. V initial squared will cancel out. If you don't see that, then I can rewrite this as numerator is V initial squared, V initial squared, messed up that too pretty badly, over G moon, times the reciprocal of the denominator. If I divide by a fraction, that's the same as multiplying by its reciprocal, so times G Earth over V initial squared. So V initial doesn't even matter, and that's why I didn't even bother solving for it. We could have solved for it a while ago, but there was no need to do that. I don't need the numerical value of V initial in order to do this. The only information I need is the ratio of G Earth to G moon. And G Earth over G moon, well, that's going to be equal to, let's see, delta x moon over delta x Earth is equal to G Earth over G moon. That's G Earth over, they told us that G moon is 1/6 of G Earth. So G moon is just G Earth over 6. Okay, 1 G Earth over 1/6 of itself, well, that means it's a 6-to-1 ratio, equals 6. So that tells me then that your displacement on the moon, your horizontal range on the moon, is going to be 6 times what it is on Earth. So delta x on the moon is going to be 18. We could have done this, again, using more traditional methods. We could have calculated what V initial was at some point, and then just plugged it in using delta x moon equals whatever number we got divided by G moon, and we could have calculated that way. But this is just one of those problems that shows you that sometimes holding off on plugging in the values that you know is helpful, because it allows you to discover things that you didn't realize were going to cancel out or simplify or whatever the case may be. So yeah, if your algebra skills are in need of work, I would recommend, I think I said this before, but it bears repeating, I would recommend to hold off on plugging things in just to see if anything interesting happens algebraically with any of your physics problems. Okay, so yeah, the distance, I guess, is just inversely proportional to the acceleration due to gravity. At twice the gravity, you travel half as far horizontally. At 1/5 of the gravity, you travel 5 times as far, and so on. That is what we get from this. And that takes care of that problem. What do we want to do next? Let me read through here and see what we have. Okay, this one isn't too hard, but it is important to cover because it gives us an important conceptual understanding that we need to have about projectile motion versus free fall. So it says, a ball is thrown straight upward and returns to the thrower's hand after 3 seconds in the air. A second ball is thrown at an angle of 30 degrees with the horizontal. At what speed must the second ball be thrown so that it reaches the same height as the one thrown vertically? So we have a ball that is thrown straight up and comes back down in 10 seconds. We have another ball that is thrown at a 30-degree angle, and it needs to be thrown with a velocity such that it reaches the same height as the ball that was thrown vertically. And I guess that's going to roll off the page, but the sticking point is this. This height, this H max, needs to be the same as this one. Now they gave us numbers. So they said the ball is thrown straight upward and returns to the thrower's hand after 3 seconds. But in fact, we can find a more general formula. We don't need specific numbers. So kind of following from what I just mentioned here about not necessarily having to plug in all your information. Sometimes you can discover new rules by doing that, by just continuing to do algebra instead of plugging numbers in. So let's actually try that. So basically, this object is thrown with, I guess I'm going to call it v vert for vertical. And then this velocity is going to be v proj, P-R-O-G, short for projectile. So v vert versus v proj. How should they compare in order to achieve the same maximum height? Well, for the ball thrown vertically, we know v top is going to be 0. For the projectile, we know that Vy at the top is going to be 0. So Vy top equals 0 here, and V top equals 0 there. And we can use that to figure out how we're going to make these H maxes equal to each other. So let me see. I'm going to start with the ball that's thrown just straight vertically. I'm just going to use the third equation of kinematics for this one because I have, well, I don't have, but I've got some unknown constant initial velocity here and some known constant final velocity at the top, and I know my acceleration. That's 3 pieces of information. So I'm going to do v top squared, which is 0 squared, equals v vertical squared, whatever that is, v vert squared, minus 2g times the delta y is just going to be h max. And I'm going to solve this for h max because what I want to do is write another equation for the projectile and solve that for h max, and then I'm going to set the two equal to each other. So I'm going to go ahead and solve this for h max, add 2g h max to the left hand side, and then divide by 2g, and that would give me h max would give me h max equals v vert squared over 2g. And let me, separate those from each other. So h max equals v vert squared over 2g. Now for the projectile, let me do this in another color. How about this dark blue? For the projectile, I'm going to work with just its y component. So I guess v projectile in the y direction is equal to v projectile times sine of 30 degrees. I'm just going to call it sine of theta. I'm just going to be more general about it here. Equals v projectile times sine of theta. Okay, so now I have something that I can substitute in for my initial y velocity for this component of v projectile. For the x component, I'll draw it over here, but we're going to leave it alone for now because we don't have any direct relationship between the x component of v projectile and the maximum height. So I'm going to then just use the third equation again. I'm going to do vy top squared, which is 0 squared, equals v projectile y squared. So that's going to be v projectile times sine of theta, the whole thing squared, and then plus 2 acceleration delta y, that's going to be minus 2g, and then the delta y's, we require it to be h max. We require it to be h max. Okay. So add 2g h max to both sides and divide by 2g, and very similar to what we did in the vertical case, in the pure vertical case over here, h max is going to be v projectile squared times sine squared of theta. I just distributed the square over this multiplication, divided by 2g. All right, so these h maxes need to be equal. These h maxes need to be equal to each other. So I'm going to set this equal to this and figure out what the ratio of v vertical and v projectile have to be in order for this to work. And I guess I'm going to take advantage of that last little corner of free space I have on this page. It's better to have it all on one sheet instead of having to constantly flip back and forth. So v vert squared over 2g equals v proj squared sine squared over 2g. These cancel out, so it doesn't even matter what planet you're on, as long as both objects are, on the same planet, or star or moon or asteroid or whatever. And I can just take the square root, I guess, and simplify this. V vert equals v proj times sine theta. If I divide both sides by v projectile, if I divide both sides by v projectile, then I get sine theta equals the ratio of the v vertical over v projectile. So I get Switch colors here. What color have I not used in a while? I guess purple. So I get V vert over V proj equals sine theta. So in our case, sine theta, sine of 30 degrees, is exactly 1/2. So V vertical is exactly 1/2 of V projectile, or in other words, this projectile would need to be fired at 2 times whatever velocity V vertical was thrown at. And if you use that number, then what essentially drops out of this is that for a projectile to reach the same maximum height as an object thrown upward, it doesn't matter what its horizontal component is doing. You just need a V initial to be such that its y component is equal to this. So V projectile sine theta, this over here, as long as this is equal to V vertical, that's the takeaway here, then it will reach the same maximum height. And you can play around with this relationship to see mathematically how that works out. We've already done all the math. Now all you have to do is just plug in numbers and check it. Just test it out for yourself and convince yourself that this is true. And I think that's all I want to do with that problem. I know they wanted a final number, but I'm not too concerned with that. I think you guys should have enough skill by this point to calculate that on your own. I just wanted to do this problem to illustrate that one concept. A projectile will reach the same maximum height as an object thrown straight up if its initial velocity has a vertical component that is the same as the velocity of an object thrown straight up. And of course, if they're both on the same planet or moon or star or whatever. Okay, what do I want to do next? Here it is. The bane of every student's existence. Already used that side of that sheet, so let's grab another one. Okay, this problem drives students crazy the first time they see it. So it says a 2-meter tall basketball player is standing on the floor 10 meters from the basket. As shown in the figure, I will draw it. So they have basketball player, hands in the air, they just tossed the basketball. They're standing delta x equals 10 meters, delta x equals 10 meters away from the basket. So I guess I'll draw the basket over here. Anyway, I'm not going to make it super detailed. I'm not going to draw a full backboard or anything. We'll just draw that and pretend it's a full basketball basket. And that basket is 3.05 meters from the ground according to the diagram. 3.05 meters. And the basketball player is, of course, 6 feet tall, or 2 meters, give or take. So 2-meter tall basketball player standing on the floor 10 meters from the basket, as in the figure. If he shoots the ball at a 40-degree angle with the horizontal, at what initial speed must he throw the basketball so that it goes through the hoop without striking the backboard? The height of the basket is 3.05 meters, and of course we can assume, as we have been assuming, that air resistance is negligible. We didn't really talk about how air resistance affects projectile motion, but I would hope that you did the homework from, 2 weeks ago, where I had you look at a simulation, and there was even a video that gave you a couple of pointers on what to try out in that simulation. And I can already see that my scale is quite off here. But yeah, the ball is thrown at some initial velocity, which we do not know. We do know that it's thrown at a 40-degree angle, though. And it's supposed to land in this basket. So the question is, for what V initial will this shot work out? For what V initial will the shot work out? Okay. Delta Y is the first thing that I want to get from this. So delta X was already given as 10 meters. Delta Y we have to calculate a little bit, but it's not too bad. So if this initial height is 2 meters, and we're going to a height of 3.05 meters, then delta Y is going to be the difference. 3.05 minus 2 is going to be 1.05 meters. So that's going to be delta Y. Okay, where do we go from there? Unlike the tennis problem that we did last week, we actually do have to combine equations from both x and y here. So let's see how that's going to work out for us. We know delta x, we know delta y. We can do... I want to do second equation in y and also second equation in x. So here is the problem. With the tennis problem from last week, we had our delta y had us at the peak of the trajectory where we knew Vy final. Here, we don't have that. Our delta y of 1.05 puts us at a point where Vy final is definitely not 0, and we have no clue what it is. Also, to make matters worse, we don't even know what this maximum height is. We don't know what delta y max is, so we don't have the same options that we did for the tennis problem. So I'm going to do delta y equals Vy initial times t, and then minus 1/2 gt squared. If I plug in acceleration equals negative g, that's where the minus comes from. Okay, and I don't want to use the third equation here for delta y. I definitely want to use the delta y, so my options would have been second and third equation. The problem with third equation is that it also uses Vy final, which is yet another thing I don't know. And my goal is to calculate V initial, which is related to Vy initial. So second equation is the best choice since it uses something I know, delta y, and also involves something that I'm trying to figure out, V initial. This Vy initial is really just Vy initial is just V initial times sine of 40 degrees. So it's really just v initial times a number you can get from your calculator. Okay, so that takes care of my vertical dimension, but I don't know v initial and I don't know t. I have two unknowns here. And the first equation and third equation would require me to figure out Vy final, which is just introducing another unknown, so those are dead ends. So my next option is to work with delta x. I know delta x is equal to Vx times t, which looks like it's introducing more unknowns because now I don't know Vx, but Vx is equal to V initial cosine of 40. So in reality, the only unknowns across these two equations are V initial and t. Two equations and two unknowns, I can work with that. Two equations with the same two unknowns, I can work with. So let's see. I want to rewrite both of these with Vx and Vy initial substituted. So I'm going to write, I guess I'll do it over here, delta y equals, I'll just call it theta for now, V initial sine theta times t minus 1/2 g t squared, and then delta x is going to be V initial cosine theta times t. I'm not plugging in the numbers I have because I want to derive an equation here, very much like what I did with the previous two problems. I'm trying to practice what I'm preaching here. So if I have two equations and two unknowns, my options are substitution, graphing, or elimination. Elimination doesn't look like it's going to work here. So substitution is going to be the way to go because I'm not going to be graphing anything anytime soon. So I can either substitute for V initial or substitute for t. The smarter choice would be to substitute for t. I talked about this last time. What you would do is you would take delta x and divide by the V initial cosine theta. You'd get an expression for t, which you could then plug into both here and here in the delta y equation. So rearranging this, I would get delta x over V initial cosine theta equals t, and then I would take this and I would take this expression and plug it into t here and here, and that would give me delta y equals, this is going to look complicated, but we will get through this, V initial sine theta, V initial sine theta, I could have written that a little more clearly, times t becomes delta x over V initial cosine theta, minus 1/2 g, and then t squared, here we go, delta x over V initial cosine theta all squared. Let's square that out and do some simplification where we can. Also, speaking of simplification, V initial over here cancels out. V initial over V initial cancels. And then sine theta over cosine theta reduces. Sine of theta divided by cosine of theta is equal to tan of theta, as you might remember from back when we were doing Unit 0, when we were talking about math skills. Or more likely, you remember it from your pre-calculus course if you had that. So that's another simplification over there. So we've got delta y is equal to, I'm going to write the delta x first, so delta x, and then sine theta over cosine theta is tan theta. and then minus 1/2 g. I'm going to have delta x squared over the denominator squared is v initial squared, and then cosine squared of theta. Some people will write this as, they'll rewrite the 1 over cosine squared theta as secant squared of theta. Those who haven't had pre-calculus yet might be confused by this, but 1 over cosine squared theta is defined as something called secant squared of theta. So if you see that in a textbook or something, that's what it means. And on a related note, if you see cosecant, so secant of theta is 1 over cosine, cosecant of theta is equal to 1 over sine. And there's also something called cotangent of theta, which is equal to 1 over tangent of theta. And since tangent of theta is sine over cosine, you can also say that cotangent of theta is equal to cosine over sine. So you might on rare occasions come across these, so it might be useful to learn them, but you don't have to use them yourself if the problem doesn't mention them. Not the biggest priority, but it's definitely something worth learning. Like, make a side note of it, and after you're done studying all of the more important stuff, maybe go back and look at things like this. But 97-ish% chance you can get away with not knowing this. So prioritize the more important things first. Lost my train of thought. Where do I want to go from here? So we are trying to solve for v initial. We're trying to solve for v initial. But I want to pause and look at this equation for a moment. So this equation, you don't have to memorize it. It's more of a shortcut equation, and again, you don't need it because, we derived it from our base equations. If you ever encounter a scenario like this, instead of having something this complicated memorized, you could just follow the same steps, which sounds daunting, but once you practice more of these, you'll get comfortable doing that. And you won't have any trouble anymore with just doing all this algebra. It'll go by much quicker. But one thing I do want to call your attention to with this equation is you've got delta y, which is a variable, delta x, which is a variable. Well, I guess over here they're constants, but what I'm trying to get at with this equation is that this equation explains why the shape of the path of a projectile is a parabola. So this equation shows you that the y and x are related by a quadratic equation. Y is equal to some constant times x squared plus some constant times x plus potentially a third constant. This would be the definition of a quadratic equation, which you know has the shape of a parabola. So how do we see that here? Well, you'd have your variables would be y and x, and so you'd have y equals, we've got x times tan of theta. So tan of theta, whatever your theta is, it's going to be some sort of constant initial angle. So that tan theta is basically going to be your b in this expression. And then minus 1/2 g over v initial squared cosine squared all times delta x squared. So the minus 1/2 g over v initial squared cosine squared, all of that stuff is essentially one constant, right? You're just going to have one v initial. It's not going to change as you go. Once you've launched your projectile, whatever that initial speed is, that's it. It's set in stone for that projectile. And cosine squared theta depends on your angle, which, again, you can't change your launch angle after you've launched the thing. So all of this stuff can be combined into a constant, and that's going to be your A. And what about your plus C? Well, your plus C is going to come from the fact that delta Y is equal to your Y final, or just Y, minus your Y initial, or Y0. And you can add that to the right-hand side of this equation, and that will be your plus C if there is any. Otherwise, it's just going to be 0. But the point is, yeah, this equation shows a quadratic relationship between delta Y and delta X. And in fact, whenever you get asked a question about the shape of the path of an object, the shape of an object's trajectory, what you're going to want to do is find an equation that relates your delta y's and your delta x's to each other directly, and then see what form of equation that is. If it's this form, then obviously the path is going to be a parabola. If you get an equation of the form of a linear equation, then you know the object moves in a straight line, and so on and so forth. So that's something to remember. Shape of path is determined by finding a direct relationship between y and x, and you do that by eliminating time. If you eliminate time, and really any other variables, it's not just time, but over here time is the thing that varies as you go. Anything that varies as the object moves other than x and y need to be removed and rewritten as expressions involving x or y, and then you'll end up with an equation that will tell you the shape of the path. Okay, now that all that is done with, let's get back to solving the problem at hand. I'll go ahead and scribble this out. So our problem at hand says we need to find v initial, so I'm going to go ahead and add all this to the left-hand side, and I'm going to subtract the delta y over to the right. So I'm going to have 1/2 g delta x squared over v initial squared cosine squared theta is equal to delta x tan theta minus delta y. I added all this to the left and subtracted the delta y over to the right. Okay, I want to then multiply by v initial squared. I want to multiply by v initial squared on both sides. That gives me 1/2 g delta x squared over cosine squared equals delta x tan theta minus delta y, all in parentheses, times v initial squared. And I'm not going to distribute v initial squared because I don't need to. I can now just divide by delta x tan theta minus delta y over to the left-hand side, and I have an expression for v initial squared. I'm going to have 1/2 g delta x squared over cosine squared all times 1 over delta x tan theta minus delta y. And that is going to equal v initial squared, and then I can take the square root of this expression and solve for my v initial. Do I have to wait until it gets this ugly to plug in my numbers? No, but like I said before, if you do hold off on plugging in your numbers, at the very least, you get to practice your algebra skills, which is really important for physics, as I've iterated time and time again. And you might discover some simplifications. Over here, I guess there's nothing else left to simplify. We already did our simplifications back up here. But yeah, so I'm just going to go ahead and plug in the numbers I know. So v initial squared, we've got 1/2 9.8 10 squared over cosine squared of 40. So on your calculator, you would just do cosine of 40 times cosine of 40 to be on the safe side. Or if you really wanted to, you could put parentheses and then cosine of 40 and then close the parentheses and then square. So that's how you would do cosine squared on a calculator, in case this is the first time we had to do it. I feel like we've done it before, but I might be misremembering. Anyway, 1/2 times 9.8 times 10 squared over cosine of 40 times cosine of 40, and then all that times 1 over 10 tan of 40 minus delta y is 1.05. Okay, and plugging all that in, I get 113.745263 is equal to v initial squared, and if I take the square root of that, I'll take the positive square root since we're just looking for a magnitude, I get 10.665, which I will round to 10.67. So I get v initial equals 10.67 meters per second is what the ball must have in order to successfully land it into the basket. And there's the basketball problem. So you're going to end up with an equation that looks like this. Anytime you are asked to calculate the initial speed of a projectile given its delta x and its delta y and its launch angle. That is where you can expect to do this. So anytime you see a problem that gives you delta x and delta y, start mentally preparing because you might end up having to do this. Okay. Where to next? Here's another doozy. Actually, I think I will save that one for later. Let's do this one first. It says, by throwing a ball at an angle of 45 degrees, a girl can throw the ball a maximum horizontal distance of capital R on a level field. How far can she throw the same ball vertically upward? Assume that her muscles give the ball the same speed in each case, and it also asks us whether or not that assumption is valid. Okay, so we have an object thrown at a 45-degree angle, a ball thrown at a 45-degree angle, on a level field. What that means, for those who aren't that good with their English, is that the field is flat. When we say that a space or an area is level, that just means it's all at the same height. It's all even. It's flat. So they called this distance r. We know it as delta x max. And they're asking, what if, so they have some sort of v initial, we don't know what it is. And then the question is, what if the ball was thrown straight upward with this v initial? This is not the same as the problem we did earlier. It's not the same as this problem. Over here, v vertical and v projectile are two different values. But in this problem, it's asking us if v vertical and v projectile are the same value, what are the heights going to be? What's going to be the difference between the heights? So in that other problem, the heights were set to be the same. Here, the initial speeds are set to be the same and the heights are going to be different. So if the ball is thrown vertically upward, how high can it go? And I guess we're going to need to express that in terms of this r, because they didn't really give us any other information. Even v initial was not given to us. This is just something I made up and introduced to the problem for the sake of, being able to do some math with this. But in general, whenever you encounter problems like this that don't give you actual numbers to work with, I like to call these expression problems. I like to call these expression problems. What you want to do, what they want you to do, is produce an expression, a mathematical expression that uses whatever values they gave you to work with. Express things in terms of what they gave you, and you're also allowed to use known constants such as g, or if you end up with fractions like a 1/2 or a 1/3 or a 3/5 or whatever, that's also okay to have. But you are absolutely not allowed to have any new unknowns that you introduced to the problem. So I introduced v initial as an unknown to this problem. My final expression needs to have this eliminated. And if I introduce anything else later, that needs to be eliminated too. So we want h is what it's asking us for, and this is, or h max rather, and they want this in terms of the only thing they gave us, which was capital R, plus constants if need be. That is what they're looking for. I messed that up really badly. Sorry about that. Okay. So I guess the first thing I want to do is find an expression relating v initial directly to r in the projectile case. We already did this before, actually. We already did this before. In the projectile case, actually, no, we didn't, did we? We did not do it in terms of, Oh, actually, Yes, we did. Delta x is equal to v initial squared over g. Yeah, we did already do it. I mean, it doesn't hurt to redo it. It doesn't hurt to redo it just so we can practice the math. Yeah, I'll redo it real quick. So I'm going to do... I'm going to do this, split it at the top, and say that Vy top is equal to 0. And I'm going to say Vy initial is going to be V initial sine of 45. So V initial sine of 45 is equal to Vy initial. And then I'm going to do the time to rise. I'm just going to use the first equation here. So Vy top is 0 equals Vy initial, which is V initial sine 45, plus acceleration times time, so that's plus negative g times t rise. And that gives me t rise equals V initial sine 45 over g. Just add t rise to the left, and then divide by g, and you're good to go. So t rise is going to equal V initial sine 45 over g. And then we need to multiply that by 2 to get the total time that we're traveling so that we can relate that to r. So r is going to be our delta x max. R equals delta x max equals Vx times t total, the total hang time. And Vx we know is just V initial cosine 45, so that's V initial cosine 45 times the hang time is 2t rise is equal to 2 times V initial sine, that is not how you write sine 45 over g. Okay, cosine of 45 times sine of 45, if you put it in your calculator, is going to be 1/2 multiplied by the 2. That all cancels out. And you're left with V initial and the g. So V initial over g times V initial is V initial squared over g. So there's that derivation again. It doesn't hurt to see it multiple times. And hopefully the next time you can do it all by yourself. Okay. So V initial squared over g is equal to r. So now that I have that, I can say V initial is just equal to, let's see. Now that I have r equals V initial squared over g, I can multiply both sides by g, and I will get r times g is equal to V initial squared. Okay, so now I can take this information to the vertical situation. If I throw something up with initial velocity V initial, what's the maximum height that it reaches? I can take advantage of the fact that V at the top is going to be 0, and I can use the third equation here because I know V top. I have an expression for V initial, and I know my acceleration, so I've got 3 things I can work with and 1 unknown thing. Let me switch to, what color have I not used in a while? Red. So third equation of kinematics would give me V top squared is 0 squared equals V initial squared. And then plus 2 times acceleration times displacement. So that's minus 2g. And then delta y, which is going to be my h max that I'm solving for. V initial squared is equal to rg. So if I add 2g h max to both sides, 2g, let me go ahead and separate those, 2g h max is equal to v initial squared, which is just rg. The g's cancel out, so it doesn't even matter what planet you're on. And divide by 2, and we get h max is equal to r over 2. If you throw something at a 45-degree angle versus throwing it with the same initial velocity straight up, you will reach a farther distance throwing at an angle than you would throwing straight up, which makes sense because if you're throwing straight up, you're putting all of the initial velocity up against gravity, which is not good. When you throw at an angle, only part of your velocity is going to have gravity subtracting from it, and then you're going to have a horizontal part of your velocity that you just get to keep as long as there is no air resistance. So yeah, this does not surprise me that the maximum height is going to be a shorter distance than the horizontal range with the same initial velocity. Or rather, with the same initial speed, I should say. If I call them the same initial velocity, that implies that it's the same direction, which is not true. Gotta be very careful with the wording. Okay. Anything else I wanted to comment on for this problem? I don't really think so. Well, there is one thing. So, they do mention this 45-degree angle. Now they've mentioned it, what, twice? And there's a reason for that. If you played around with the simulation, especially with air resistance turned off from, 2 weeks ago, then you might have realized that a 45-degree angle gives you the maximum horizontal range. You might have discovered that. There's a reason for it. I don't know if I want to go over the proof. There's an algebraic proof and then there's a more calculus-based proof. But I think you guys can figure that out on your own. Actually, one of the problems I have lined up might actually have us do that anyway, so we'll see. Anyway, that's it for this problem. Now let's go back to that other problem that I skipped over. This one is rather interesting. So, this one says, in a very popular lecture demonstration, a projectile is fired at a falling target, as in the figure, and they've drawn a guy holding a gun, holding some sort of rifle. Aimed directly at, I guess they drew a ball. And what it says is, a projectile is fired at a falling target, as in the figure. So this thing is going to be released from rest the moment the trigger on this gun is pulled. And yeah, the projectile leaves the gun at the same instant that the target is dropped from rest, assuming that the gun is initially aimed at the target. Show that the projectile will hit the target. One restriction of this experiment is that the projectile must reach the target before the target strikes the floor. That's just additional information that they put in parentheses, but we're going to assume that the projectile is dropped from high enough that there's enough time for the bullet to reach it before it hits the floor. So in addition to what they've already drawn, they've also drawn this. So they've drawn whatever this angle is, they called it theta 0. And they've also drawn the trajectory of a projectile like this, and they've also drawn the ball going down like this. And basically they're claiming that if the gun gets fired straight at the target just as it's released, then even though the target falls, so does the bullet, and the bullet just so happens to fall in such a way that it still hits the target at the end. So we are going to show that the projectile will hit the target. That is our goal. Okay, how do we even begin with a problem like this? They didn't really give us much information to go off of. I mean, I guess the other thing they have in this illustration, let's do it in green. They called this V0, and they told us that this target starts from rest. They told us that this has V initial equals 0. And that's all we have. Well, what we want to do is figure out the final position of both objects. We want to figure out the final position of both objects. So this object is going to have some sort of delta y this way. I'm going to call it delta y ball. And this object is going to be fired, it's going to act as a projectile. It's going to have a delta y from wherever its launch point is in the gun to here. So it's going to have a delta y, I'll call it delta y bullet. Delta y bullet. Maybe bullet. You know what? Fine. I feel like it's too long of a word to keep writing over and over again, but I'll deal with it. So delta y ball and delta y bullet. We need to show that they both end up in the same position. We need to show that this height is the same. So what I want to do is I want to approach this in two ways. I want to figure out where this position is. I want to figure out where this final position is. I'm going to call it y final. I want to show that y final, as calculated from our physics equations, is going to be the same as y final that we get if we just do some geometry here. So which one do I want to do first? It doesn't really matter, but let's do the physics first. Let's do the physics first. So delta y ball, I can just use the second equation of kinematics for this. Delta y ball equals v initial of the ball times t plus 1/2 gt, or minus 1/2 gt squared. So it's going to be v initial times t minus 1/2 gt squared. V initial times t, that's just going to be 0. So delta y ball equals negative 1/2 gt squared. Okay, what about delta y of the bullet? Delta y for the bullet is going to be, Delta y of the bullet is going to be whatever Vy initial is. So Vy initial of the bullet, I guess I'm going to call that Vy0 is equal to V0 times sine of theta 0. So it's going to be V0 sine theta 0 times t minus 1/2 g t squared. Okay, and I'm going to rewrite delta y ball and delta y bullet. So I'm going to say delta y ball is equal to, well, I guess this would be H initial. So delta y ball would be y final minus this H initial. So y final minus H initial. Actually, I can just call it H, because H final is just going to be 0. Actually, it's not even H final, it's just going to be H at the bottom. I'm going to call that 0. So we have an H all the way up here. Over here we have a height of 0, and then over here we have y final. So yeah, y final minus, I'll just call it H for delta y ball is equal to negative 1/2 g t squared. And then for the bullet, I'm going to do delta y bullet would be y final for the bullet minus its initial height is 0. So y final minus 0 equals V0 sine theta 0 all times t minus 1/2 g t squared. I can go ahead and substitute for minus 1/2 gt squared. I can substitute y final minus h. So let me switch colors for this. What color have I not used in a good bit? I don't even know. It's not like I do the best job keeping track of all this. I'll use this color. So minus 1/2 gt squared replaced by y final minus h. So y final minus 0, or just y final, equals V0 sine theta 0 times t. And then minus 1/2 gt squared becomes plus y final minus h. I can cancel a y final on both sides, and I will add h to both sides to get h equals V0 sine theta 0 times t. Of course, here t, I should have commented on this earlier, t should be the same for both the ball and the bullet. The bullet was launched, was fired at the exact same time that the ball is released, so they should both have the same t's. There's no need to have separate stopwatches for them, since both of them start moving at the same time. Okay, so I've got that expression. So this we got from physics. Okay, this is what we got from physics. Now, I want to do another calculation from geometry, which is actually still going to use some physics, but I want to show that we end up with the same expression. So now from geometry, what I want to do is, well, I want to figure out what this h is. I want to show that we still reach this same conclusion. So I want to figure out what this h is. And the way I would go about doing that is I would calculate whatever this distance is. I'll call it d. So d is equal to what? It's going to be equal to, if the bullet had just moved straight here, it doesn't, but if it did, it would travel this distance d. So I'm going to act as if the bullet moved in a straight line just to calculate what d is. If you moved at a velocity of v0 for a time t, wait, would it be for a time t? Let me think this through. It would have to be, right? Yeah, because I'm assuming that the bullet moved in this direction instead of falling, so that shouldn't change the amount of time it's moving. Okay, yeah, so d is equal to v0 times t. Okay, so then if I want to calculate h, well, I have a right triangle. I have a right triangle whose lengths are d and then h, and then whatever this delta x is. And I know that this is theta 0, so I can say that h is equal to d times sine of theta 0. Oh, if h is equal to d sine theta 0, then h is equal to v0 times t times sine of theta 0. But wait a minute. This is the same as v0 times sine of theta 0 all times t, which should look familiar. So the result we get from geometry equals the result that we get from just regular projectile motion equations. So yeah, this is all the proof we need that the bullet and the ball land at the same place. You could go back and, let me think here. You could go back, I guess, one step over here, or actually 2 steps. You could go back to here, actually. You could go back to here and take this conclusion that h is equal to v0 sine theta 0 times t and plug it in here, and then add this over to the right-hand side to show that you get the same y final between these 2 equations. And yeah, you would end up with the bullet and the ball at the same height at the same time. So you're good to go. You've proven that they will be in the same place, which means the bullet does actually strike the target. This one is admittedly a bit of a headache when trying to first wrap your head around how this counts as a proof. You will need to think about it for a little while. I know I sure did the first time I did it. But yeah, there you go. Definitely one of the tougher problems. I don't think they would, well, it might be fair game for the AP exam. I don't want to say it's impossible for them to give you something like this, because algebraically it's doable. It's just understanding it is a bit of a doozy. This would be conceptually one of the harder FRQs they could give you. It's like in that upper range in terms of difficulty, not because of its algebra, but just because of the conceptual understanding of the proof. Wow, look at all those chat disconnected messages. I'm going to take another screenshot of this. I need to figure out what is wrong with this. The more that time passes, the more of those messages I see. I don't know if it's because I set things up incorrectly, or if YouTube is just having a bad day, or what, but I've never seen anything like this before. Okay, next problem. What do I want to do next? Here's something that I was alluding to before, and I think... will this be our last problem? I'm looking ahead and I don't see anything else I would want to prioritize, so yeah, I think this is going to be our last problem for today. And I guess this means congratulations are in order. We have reached the topic of force for next time. Although, maybe I shouldn't be speaking too soon. Maybe the stream will cut off or something when I least expect it. Anyway, it says, a projectile is fired with an initial speed v0 at an angle θ0 to the horizontal, as in a figure that I don't have on this page. But that's okay because I can picture it in my head. When it reaches its peak, the projectile has xy coordinates given by capital R over 2, comma, h. And when it strikes the ground, its coordinates are capital R, comma, 0, where capital R is called the horizontal range. Part A says, show that the projectile reaches a maximum height given by h equals v0 squared times sine squared of θ0 over 2g. So, here's the angle θ0, here's the initial speed that they called v0, goes into the air, reaches some maximum height, comes down. They said the coordinates here are going to be r over 2, comma, h, and then the coordinates here would be r, comma, 0. Just x, y coordinates. They decided to use coordinates for some reason here. And it says, show that the projectile reaches a maximum height. So for part A, prove, show, h equals v0 squared sine squared θ0 over 2g. This might look familiar. This might look familiar because, well, we did it not too long ago. We said r is equal to... No, wait a minute. Did we? I don't think we did. No, I don't think we did. We kind of did, but we calculated it for like the end point and not the halfway point. Okay. We might actually have some work to do after all. I can't just skip and reuse old work. That's fine. So that's part A. And then part B is going to require a trig identity, which you would have to remember from pre-calculus. Part B says, show that the horizontal range of the projectile is given by, so show B, prove, show that the horizontal range is equal to, and they say v0 squared sine of 2 θ0 all over g. Okay, those are the two things that they want us to prove. Okay, let's find that h first. So to get h, I would need to take advantage of the fact that Vy at the top is going to be 0. And what I can do is, well, same thing I did to calculate t rise before. Actually, do I even need t rise? No, I think I can just use the third equation of kinematics here. Yeah, it should be Vy top squared, which is 0 squared, equals Vy initial squared, which is going to be V0 sine of theta 0, plus 2 acceleration delta y. So that's minus 2g. And then my delta y is just going to be this capital H. Or not capital, lowercase h. Okay, and then add 2gh to both sides, divide by 2g, and we're done. Add 2gh to both sides, 2gh equals, that's going to be v0 squared sine squared, if I distribute the square over the multiplication, and divide by 2g, and we have it. Okay, that wasn't too bad. So h equals v0 squared sine squared theta 0 over 2g. The nice thing about these proof problems compared to expression problems is that you actually know what you're supposed to get. So my advice for proof problems is look at the thing you're supposed to get, and that will often give you clues on what to try. I see a v0 squared, for example, so that might guide your thinking towards using the third equation of kinematics, since it has the squared velocities in it. Things like that. We'll get to see more proof problems as we go through the course and see how we can kind of take advantage of the final statement we're supposed to derive in order to get hints on how to even work towards deriving it. But anyway, part B. Show that the range is equal to v0 squared sine of 2 theta 0 over g. So we had the equation earlier that could be turned into this. So we did do that work before. So what I want to do is calculate, well, I've already done it twice before, so I don't think it's cheating to just copy it over this time. We had, for the symmetric case, we had the range. You have to calculate t rise first, which is going to be v initial times sine of your theta over g. So that's going to be v0 sine theta 0 for our problem over g. And then your horizontal range is going to be vx times the total hang time, which is 2t rise. So we would have vx becomes v initial cosine the angle, and then 2 v initial sine of the angle over g. Cosine 45 times sine 45 times 2 all got eliminated. This time that's not going to happen because, well, it's not 45 degrees. That was just a special case. So v initial times v initial would be v initial squared. So I'm going to do r equals, we're going to have v initial times v initial as v initial squared. And then, so we took care of that, we took care of that. And then we've got 2 sine theta cosine theta over g. 2 sine theta cosine theta over g. So times 2 and times sine theta times cosine theta over g. And also, I should call this v0 because that's what they call it for this problem, and these are theta zeros. Okay, so for those who took pre-calculus, you should be able to recognize 2 sine theta cosine theta is equal to what? 2 sine theta cosine theta is equal to sine of 2 theta 0. If you didn't realize you were supposed to use this trig identity, all you would have to do is look at what you have here and compare it to the thing you're trying to prove, and you'll see the v0 squared, that matches, the over g, that matches, so you're left to conclude that somehow 2 sine theta 0 cosine theta 0 equals sine of 2 theta 0, and that should be the hint that you can give yourself to remember and pull this trig identity. For those who haven't had pre-calculus, I'm sorry, but this is too difficult to prove from scratch. It's too time consuming and it's just not worth it. You'll just have to wait until you learn this in your pre-calculus class. And if you can't wait that long, I would recommend just going to Khan Academy or something similar and look up their trigonometry videos. You'll have the sum and difference identities, which also require quite the long and elaborate proof. And once you prove the sum and difference identities, once you prove that sine of a plus b is equal to, oh goodness, do I even remember it? It would be sine, cosine, cosine, sine. It would be sine of a, cosine of b, plus cosine of a times sine of b, if I'm not mistaken. And then you would use this to prove that sine of 2 theta would just be sine of theta plus theta, and then if you plug in theta for a and theta for b, you'd get sine theta cosine theta plus cosine theta sine theta equals 2 sine theta cosine theta equals sine of 2 theta, sine of theta plus theta. But yeah, just this alone then you would have to prove, and that requires a little bit of analytic geometry, and we're not doing that today. So yeah, this is just something that you're going to have to know. Again, low priority, kind of like what I said, where was it? Kind of like what I said back here. Kind of like what I said back here. If you haven't learned this because you haven't taken pre-calculus already, or you haven't gotten that far in pre-calculus, these are going to be much lower on your list of priorities, because problems where you would use these, similar to problems where you would use this identity, they're so few and far between that your study time is much better spent on more important ideas and concepts. Put something like this among the last things you study. When you've really studied everything else and you know it well and you don't see much point in reviewing it again, but you still have free time and you want something, that is when I would go back and try to learn these. But yeah, there you go. So, any additional comments I want to give? So when you use this trig identity to come up with this formula, v0 squared sine of 2 theta 0 over g, when you use this formula to calculate range, this explains what you may have seen if you did the homework 2 weeks ago, where I asked you to use the PhET simulation for projectile motion and figure out if there was a pattern for launch angles. If you fire projectiles at the same initial velocity and you try a bunch of different launch angles, you might have noticed that certain pairs of angles always landed you in the same spot, always gave you the same horizontal range, and there was a relationship between those angles. They always added up to 90 degrees. So if I fired a projectile with velocity v0 at angle 30 degrees versus firing at 60 degrees, they would both land in the same place horizontally, assuming you had the air resistance turned off. And 40 and 50 would give me the same, and 20 and 70 would give me the same, and so on and so forth. The proof of that relationship is actually in this sine of 2 theta. The proof of that relationship is in this sine of 2 theta. So if you know your pre-calculus, then follow along with me here. Sine of 2 theta. So if I were to solve this for theta, if I were to do sine of 2 theta equals, I guess I would multiply the g and divide by v0 squared to get the sine 2 theta by itself. So it would be rg over v0 squared. If I take the inverse sine of this, if I do 2 theta 0 equals arcsine, or inverse sine, of rg over v0 squared. Your calculator will only give you one result, but in truth you get two different results. There's another result that your calculator doesn't account for. This is very similar to the square root problem, where your calculator will only give you the positive root, and you have to remember that the negative square root is an option. Same thing for the inverse trig functions. Sine inverse will only give you angles between negative 90 degrees and positive 90 degrees. But there are actually two angles that might have this same value. I would assume, no, not assume, this value is definitely positive. Range is going to be positive, g is positive, and v0 squared is positive because, well, it's squared. So yeah, for positive angles, if you remember your unit circle, there are two angles that would have the same sine theta. So for positive thetas, you would have, let's say for example here, you have some sort of theta, and then sine of theta is whatever the y value is over here. Well, there's another place on the unit circle that has that same y, which would be over here. And it would have a reference angle of theta with the negative side of the x-axis. So that angle would have to be, let me do red. That angle would be equivalent to 180 degrees minus theta. So in fact, sine inverse, while sine inverse will give you whatever this smaller theta is, you have to remember that 180 minus that theta is an option. So 2 theta 0 equals sine inverse of rg over v0 squared, or 180 degrees minus sine inverse of rg over v0 squared. And then if you divide by 2, then theta 0 is going to be 1/2 sine inverse of this expression, or 1/2 times all this, which would be 90 minus 1/2 sine inverse of the expression. And there you go. That's why they add up to 90, because when you distribute the 1/2, this 180 degrees becomes a 90. So you're going to get an angle or 90 minus an angle. Hopefully that made sense. I'm sure you can reflect on that some more and piece it together. I don't think I have to write those last two steps out. Well, last one step actually. I think you can take it from there. But yeah, we are done with projectile motion. At least for now. I mean, we'll probably get to do some review once we're done with all the course material. But I think I've presented enough for now that you should be able to learn from the strategies I showed off. Definitely keep looking for challenging problems and review regularly. Look through the textbook. I guess one thing I could have done was look at the problems that I marked with a star in the homework list, because I think I had a few of those for the projectile chapter. But maybe I'll go revisit those during a review, or maybe I'll do that during like my traditional office hours or something like that someday. But for now, I think this will have to do. So next time we are going to do force. So what I would like everyone to do before next week is, let me see if I can switch to this tab. So for next time, let me see. Yeah, we're going to go over the definition of force, and we're probably going to discuss Newton's first law, and maybe we'll reach Newton's second law as well. Actually, I don't think we'd be able to do much before Newton's second law anyway. Discussion of g-forces, I don't think I'm going to discuss that too much, if at all. There are some videos going over that stuff. You should be able to understand the ideas from there. And I think I'm just going to go over a few of the forces that we will encounter in physics. I'm probably going to spend force, first of all, I should have said this at the beginning. Force, at least in my opinion, is the most important chapter in all of physics. I truly believe that once students have a full conceptual understanding of force, which is easier said than done, and a lot of people do make it through physics without this full conceptual understanding. They can even get 5s without this full understanding. But I truly believe that if you take the time to fully wrap your head around the concept of force, you will have no trouble figuring out any other physics topic, any other physics course ever in your life. Other people will argue that energy is the most important idea in physics, but I think it's force. So I like to spend more time than usual on force, and that will probably be reflected in the streams, but we will see. So I'm going to probably dedicate a lot of time to just going over each of these individual types of forces and talking about like their intricacies. I think friction, for example, is going to be in a separate stream. Definitely not going to be next time. Almost definitely is my prediction. Spring force is, well, I guess spring force is going to be something I touch on a little bit, and we'll dig deeper into it when the energy chapter comes into play, which is the next chapter after this. But yeah, normal force, applied force, tension force, conceptually understanding them. Same thing with friction. I just really like to spend a lot of time making sure we understand those. And then for forces on multiple interacting objects, Newton's third law, I have a whole entire spiel about Newton's third law. You can even find it already on my channel. I think I titled the video something like 7 Things Your Physics Teacher Never Taught You About Newton's Third Law, or something like that. So that's going to be a video to watch. Actually, I think it is the last video in this list of 6 videos on misconceptions. But yeah, so you probably want to look up to here for next time. I think that will be enough prep for next week's topics. And we might introduce free body diagrams as well. For the videos and resources, I guess that would be 1, 2, 3. Maybe we'll get to this. And then for practice, oh, these are my PDFs. For practice, basic vector addition of forces, that's just a review of vectors in case you haven't done that in a while. I mean, we have been working with vectors in this projectile motion chapter, but we didn't really do a lot of vector addition. We just did a lot of decomposition, so vector addition may need some review. Free body diagrams, if we get to that. One-dimensional force problems, we're going to have to cover a few types of forces before we can do that. At the very least, normal force and gravitational force and maybe tension force would be needed to do this. And for the readings, chapters 4 and 5, let me see the difference between the two. So chapter 4 has first law, second law, third law, tension, normal force. Okay, so yeah, it looks like we're going to be mostly in chapter 4 next week, and I think chapter 5 is what adds friction. Okay, friction, drag forces we don't really need to do for Physics 1. Physics C students, you will need to understand drag, so once we get to that, which is probably the week after next, I'm probably going to save that for the end, dismiss the Physics 1 students, and then tell the Physics C students to stick around, and we'll talk a little bit about drag force, though not too much, because I'm going to save most of the drag force discussion for when we get to the calculus part of the course. And if you're wondering when the calculus part of the course will be, I think I already discussed that in the very first stream of the playlist, but it doesn't hurt to repeat. I teach the calculus for Physics C after I've taught everything using algebra-based methods. I think that's a better way of going about it, because then you don't have to learn math at the same time that you're learning physics. You've had enough time to really digest the physics concepts, and then you can go back and it serves as a review of the physics, and because you're already comfortable with the physics, it makes it easier to then add the calculus to it. At least that's what I find with the students I teach. I feel like that works a lot better than trying to shoehorn calculus into everything. Because what I see students do when you teach the calculus along with the physics is they'll try to use calculus on everything, even when it's not needed, and that's not good. Calculus should be like, it's the power tool in your toolbox. You don't use a drill to build a table that can be built using a simple screwdriver. You're just going to end up damaging the table because the drill is too powerful and unwieldy for you, and I don't know where I'm going with that analogy, but hopefully you understand what I'm trying to say here. And yeah, I think that is it. So reading mostly in chapter 4, and maybe try out some of the conceptual questions and the problems and exercises, I guess. If you feel comfortable after watching some of the videos, especially if you look at the worked examples, you can try some of the problems and exercises and see how far you can get with them. But we can save that until after I've actually discussed a little bit of force. So yeah, I think that will be it. I don't think there's anything else to mention. And I do feel up to doing traditional office hours, so I'm gonna go ahead and take a little break. And once I'm back, the topic I have planned is just a few calculus skills. I wanted to follow up on the stuff I was doing last time with Riemann sums, and I'm going to cover a couple of techniques for solving certain types of integrals, especially U substitution, and probably after that, like next week or the week after, we will go back to doing some more applications of Riemann sums. So yeah, Physics 1 students, you are dismissed. Those looking forward to traditional office hours, I'll be back in like 15 minutes.